It's good to see everybody on. Happy pre-holiday, happy Thanksgiving, however you want to look at it. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device. This is discussion 110, Wednesday, November 22nd, 2023. So this is 38 of the Qiskit PennyLane QML/QiML demos for this holiday week. And if you were able to turn in the first time, I did first iteration PennyLane, first iteration Qiskit, and now I'm just doing them all together. And was able to get a lot in the form of progress. Now, the first thing I want to go over is basically if you're looking to get into quantum-inspired machine learning with simulators, it's looking to be like the application for quantum computing these next several years. There's a number of tips with it. So basically, you want to get the fastest you can to begin. So you'll have a quantum simulator. Now, you've heard of these things as far as, back propagations from classical. Parameter shift is more for quantum hardware. But in specific, adjoint differentiation, when you really want to use it. A lot of times it'll be set to something else. It's supposed to be best method. So I wasn't quite sure if that's back propagation that it's set to, but anyways, adjoint in theory, if you have a quantum circuit with classical code, set it to adjoint. Many models can use lightning.qubit. When you open up a lot of these, they're just default.qubit. I think it's just to save on their compute time. And it's literally almost always a fix for faster times. Lightning.GPU is significantly faster for larger problems / data sets. It still has, to kick in a little bit. It's typically faster for smaller problems, such as the iris data set with like 150 images. Now, the way that you do this is basically you'll have a Colab account and you'll select a GPU, so an A100 / a V100, and then you're going to set in the notebook lightning.gpu, and then you're going to type in this pip install, which has, PennyLane. It's a state vector basically, but it's with a QQuantum. Now, for circuit performance, there's a lot of it still I would say experimental. I think very few people can say definitively double the circuit or halve the circuit, when to use symmetry, when to double the qubits, halve qubits, or go up by odds or go up by evens. These are the types you can do. And also you can switch the embedding type. So like Qiskit has Z and ZZ feature maps. One has entangling. It's a lot bigger, computational cost. You can also switch in primitives. So these are like your C0s, your CZs, and CYs. You can remove layers, add layers, entanglement patterns. And you can switch these standard rotational gates. So a lot of times a really good circuit for embedding is just a Hadamard and an RY gate, however many qubits. And that's good. And then you get into trainable circuits, and then it's a little bit more specific to the number of layers. And you can also do stuff with torch connector and torch layers as far as literally inserting your quantum circuit into a specific part of a torch code that already exists. So torch is definitely progressive with quantum machine learning, less so, I would say, with the TensorFlow. Now, optimizer settings work just as before, and you can actually set multiple optimizers per model. I was not aware of this until this week. And so basically you can have a separate optimizer for your, you would need one for a GANs, your generative network, your adversarial network, these types of things. And then also increasing batch size, data set size, those types of things, and weight decay, dropout, frozen layers, and regularization I'll be going over today. And this is basically if the weights get too high, it gets computationally heavy there. So it's trying to carry a ton of information on that specific weight. So regularization basically keeps or different forms of regularization try to keep the weights low. So feel free, if you have any questions, you can unmute yourself. You can also put in the chat. We'll take a break probably every 6 to go through this. So this is the first Qiskit here. And this is basically, it's an introduction to, estimator QNN and their sampler QNN. There's just different ways of using this. And, depending on the circuit, will output different weight gradients. So this upper left one is basically their stock demo, or they call them tutorials or Qiskit machine learning tutorials. The upper right one is the one that got modified previously by myself. And then this bottom one is basically a bigger circuit I chose to use six gates. So just for those, if anybody is not quite aware, we're talking about qubits. So Q0 is the first qubit, and then you all have Q1 is the second qubit. The individual gates are not physical gates, and especially for simulators, they're matrices. So it's literally linear algebra is performed on these specified qubits at different time points. So at time point 1, all qubits 6 are experiencing the Hadamard gate. Time point 2 is a fixed rotational gate. Time point 3, fixed parameter rotational gate like an embedding. Time point 3 is a trainable weight, which makes it like the AI or the machine learning aspect of the quantum circuit here. And then the last one is a different rotational gate. So basically these are trainable parameters. These are in the classical world, they're called weights and biases, but they're so-called parameters. And quantum, we'll call them rotational angles, typically, with that. Now, the second one here is basically, you can see the upper left to the upper right. Classification accuracy was increased by limiting the number of ZZ feature map repetitions. So it's not quite as correct to call them layers, because a ZZ feature map has multiple layers in it. So you'll often see this in Qiskit notebooks abbreviated as reps, REPS, and then equals whatever. So this upper right-hand one is reps equals 1. Now, what was done in this particular one is it's basically taking that notebook from the upper right-hand and changing the ansatz. So the ansatz is basically a template. And it's, in this case, I chose two real amplitudes for this to get this classifier score. But a lot of times you have to get even lower with loss to get in, say, even like a better score if you're dealing with a limited amount of data here. So you can see the distinguishing thing here is the loss, or they'll call it objective function value, which is very similar to a loss curve. So this loss curve is the best out of the 3. So that's what's unique about this specific study. Now, this next one is basically, it's a variational quantum circuit with efficient SU2. So this is another one of their, it's similar to like a real amplitudes like before. And basically what was done this time is just to increase the total number of iterations. And I was able to get the test score up a little bit. So this particular model for me was more challenging because I ran it so many times to try to get this better and better. So sometimes the next steps might be change the data set. If it came down to it, in the future, as opposed to like just for lack of better terms, like, starting over with the model. So on this particular one, that's what I got. And I tried all different repetitions, but this is what's different about this study is the 82% compared to the 79%. So, you hope to get these, great improvements in performance, but sometimes it doesn't come right away. So this next one is basically this clustering score. I was able to improve last time to a 1. So it's, in other words, it's 100% accuracy. It's a score that they put on it. And then what I did different in this one is I doubled the data. So you can see in this lower right-hand corner, there's a lot more data sets. So instead of 25 train, I did 50. Instead of 10 tests, I did 20. And then I think on this left one as well, they're marking it training score was 1. And then I could see definitely with doubling the data set size, for better separation, you always need a sufficient, training set. So a lot of these training sets are kind of small for the Qiskits. And, basically I got that 100%, or the 1 for regression score. And it's visually more apparent in that specific one as well. Okay, so this number 5 one is basically, it's a quantum GANs. So GANs is basically you have some real data and you want to basically replicate it. And the way that you do this is you have a generator, and your generator first starts off generating, based on fake data, a bunch of fake data. And over the course of the time with these two networks is that the fake data starts to look a lot more like the real data, and people want to use this for medical other purposes too. And then it just comes to question like, can we truly really trust this, if it technically started off as just random noise? So what was done first was the number of shots was decreased by a factor of 10. And then I was able to get a similar, the main one to look at is this end. So this one, you don't want the extremes. You don't want dark red and you don't want dark blue. So this one was close to that with, 10x less shots. Now, what was done on this specific one was the learning rate was decreased. So when you decrease the learning rate, it's like it's a gradient. So just imagine you have like a bunch of, it's like an egg crate carton foam. And, you could have many of those local minimums, but ideally you want to find the one that's the steepest. So the original learning rate was 0.010, and then I reduced it to 0.008. I trend to, if it's in, something like this, if it's 10, I'll either go up by, this would be 0.002 or down 0.002. So if it's odd, it's odd. If it's even, it's even. That's just what it seems. The biggest thing is like just from a screening standpoint, because you don't want to have to do so many when you're not giving it enough room to basically move. So in this specific case, it had a lower final entropy. So you can kind of see here, the left one it may have just flattened at the bottom. So you always want to see the entropy decrease in this specific model. And then this one, if I kept running it, so this is 10,000 shots. If I ran it at, 15K or 20K, this might have even worked out even better. So, that's basically, if you're stuck with a circuit, like you don't know what to change, like double gates, half gates, changing, layer types or rotational gates, definitely always check the optimizer. Okay, so this is number 6. So this is basically torch connector. So IBM Qiskit and Xanadu PennyLane both have an efficient way of incorporating with PyTorch. And I would say the PennyLane is kind of taking it further, but there's still with these different, basically you're inserting a quantum circuit as a layer in the middle of a torch neural network, like how you see this line of code is convolutional, this line of code is pooling. Well, now a specific line of code will be for the quantum circuit as well. So similar to the previous one, and actually, even though it might make sense to always decrease the learning rate, that's not always how things go. So I was able to get significantly better test loss in the last round. So -1.7 to -7. And I got that 100% accuracy. So what was done on this specific one, and I've been touching on this previous episodes, is that if you have all these trainable weights and they're kind of just like, just being optimized to whatever, it feels it is the best, you can actually bump in, like the user bumps in and say, hey, computer, don't go over a certain range for the weights. So weight decay of 0.1 will do that action a lot stronger than a weight decay of 0.001. So in this case, I set it to 0.01. And then it helped with the test loss. Additionally, I couldn't do any better than the 100% accuracy, but it's -7.51. So, it helped there. And if you watch like Andrew Ng, he's a professor at Stanford, and others too, they'll say, yeah, you really have to get into some of these other settings like regularization, weight decay, dropout, freezing layers, if you understand what they mean, because they do make a very big change a lot of the times. Now, this next one is a quantum support vector. So what was done first here is basically, the runtime was decreased a little bit. And in the bottom one is basically, I doubled the sample. So it says, 2 times the data. And in order to keep this, I used the same tau as before. So it actually ran a little faster, which I'm still trying to understand, because it could just be the Qiskit. This is a Qiskit error simulator. But in theory, if you're giving it more data, it should run a little slower. But over the course of time, Qiskit has updated the simulators from like, I think, a dual core, and then I think these days it's an 8 core. So anyways, it's good. It ran faster, and that's still, I would have to look at more things to fully understand this one. Okay, so this next one is basically, it's doing whatever's necessary to decrease the loss. And ideally you want it the lowest you can. Now, typically you get down to, a low positive number, or you can go up to a high negative number. I've seen Qiskit, I think PennyLane does that too on occasion. But what helped the most here was this regularization. And this is a SPSA optimizer. So you have to dig into all this documentation and then find out, what's kind of like, so regularization, it could be L1 or L2. So in this specific case, if it's an L2, it would do something, as I mentioned before, like limit the weights. And you could see that, obviously keeping the same accuracy, and then the loss was down to closer to 6 as opposed to the other two, which were, 11 or closer to 12. So that would, that's a pretty good bump right there. Okay, so this is number 9. And, so basically with this specific one, it's continuously training. So it took me a while to figure this out, but the yellow curve is a certain, training model. The second one picks up where the last one left off. And I had a hard time just keeping this, as you see, it gets closer to this 0.4. So basically what was most productive with this model was, again, to increase the data set size. And like, again, if it's really small, like these two top ones, I was able to increase it a little bit. So say for this red one, it's no longer red, so that gets a 93% versus 0.9 over here. And then over here, there's more that are circled, but there's also more data set. So it seems like that's just the trend with a lot of these Qiskit ones, is that they just have smaller data sets. It's more important to, get everything running. And if you're thinking in your head as far as, this is a good circuit change to make, or a good optimizer, modification to make, those types of things. But anyways, I increased the data set and then wound up with a new test score from 8.8 or 80% to 0.9. For the test score, this kind of like the metric for it. Now, this particular model is very interesting, and I would recommend reading this. So effective dimensions, and it's one of those things that, like, you can get great effective dimensions, but you got to watch out for overfitting. And it was a similar thing with other researchers with, quantum metric learning, training the embedding, and that's the only thing to focus on. And they noticed the same thing too. It's like you have to watch out for overfitting. So it's a good thing. There's local and global effective dimensions. So in this specific one, you can see that, on the right, it was, increased to about 96% for the untrained weights, the orange curve. And what was done here is basically this ROBEG. So ROBEG is basically, it has to do with reasonable initial changes to the variables. So, there's all these settings, deep inside of machine learning, and in an advanced machine learning group here in town, it's virtual, but advanced San Diego machine learning. And anyways, they'll touch on these types of things because it could literally make the difference of, up here it's 96%, or it's an effective dimension. So it's, 0.96 compared to 0.985 as the orange curve approaches that value. So anyways, I found that they say ROBEG. So ROBEG is initially set to 1. And then so I found that at this 1.14, it gave me the best as far as the highest for the train and the untrained for the, for this normalized local effective dimension. So yeah, it's called ROBEG. And I don't know if it's for other ones, but I know it's on. So this specific one is for the Cobila optimizer. So there's Cobila, there's also Atom, and many other ones. Okay, so this next one was probably my first model that I actually got this 100% training, 100% testing. And again, it's small; it's an 8-pixel image. But what did it is I just doubled the circuit. So a lot of these things, like I said, for a while, it's still, experimental. Like, even if you knew, theoretically the best, okay, I really think at this point, 100% changing from an RX to an RY, these types of things, you still need to do it experimentally, right? So it depends on the data set, like the application of it. And what helped here is basically, I was already at the 100%, but to get even lower of this objective function value is to double the iterations. And then you can see that the objective value just continues to get lower. So this is I don't know, like the third or fourth serious attempts that I've had on this model to improve it any which way, and all of these are upgradable. Changing, say for instance, it's this initial circuit gets built up to I believe it's 16 qubits. I think it's twice as many qubits as pixels. So anyways, these are modifiable. And I would say a lot of these Qiskit ones haven't seen as much attention since they first were announced. And with all the news going around, so if you haven't heard the breaking news last Monday, and actually this Monday too, but last Monday, 3 organizations saying GPUs, quantum algorithms, we're focusing on those types of things. So BASF, and they're all NVIDIA and GPUs, QQuantum, that type of stuff. And what happened this Monday too is Sandbox AQ, further said that this is different than generative AI or what exists classically, and we really think that this needs development with GPUs and quantum algorithms. Okay, so this next one is basically obviously decreasing the number of layers here decreases the runtime. So 36.48, 32.55. If you haven't done this before, you always if you're focusing on runtimes, usually performance and those like accuracy loss are the same. But for runtimes, there's an initialization process for the first run. Okay, so when you run the whole model and you're focusing on how long it took, just disregard that time. And then you always have to run a second time. And then that second time, as long as you don't change too much else in the model, should be good for comparisons of other things that you want to change. And again, so with this specific one and with the Cobila optimizer, which you're going to find a lot in the Qiskits, I changed it to 0.8. So again, the default it's RoBeg. With RoBeg is 1.0, and then this time I went less than 1.0 to get these. It's 5 nines, 0.99999, and then this shows up in the objective function value, which is similar to a loss curve, and you can see it goes a lot closer to 0 a lot quicker, and then the kind of where it flatlines, closer to 0 is earlier in the iterations for those. And are there any questions regarding any of the Qiskit models or circuits or any of these things? I hope that others have been able to get on them. And this one, it still has an issue with later in the model, but all the other ones run. And the good thing about the Qiskit is you're running in Qiskit Lab, so you don't have to worry about any costs, and unless you start doing stuff with GPUs. But the installs too, typically with the models, is you just click play, and then there's a little less of that pip install stuff, that you would get with PennyLane because they don't have a dedicated IDE. But yeah, any questions at this point?
A small question about the quantum encoder. Did you have a chance of running it on GPU?
I still have an issue with the Qiskit stuff. I put in the chat, like it's the Slack. There's a convenient way of doing it in Colab, like it's just 3 steps with PennyLane that I've got worked out to a science. But I don't. Have you or anybody else been able to do that with GPU and Qiskit notebooks?
Well, I had a problem because to encode a lot of information into autoencoder, you need to use raw feature vector, and that crashes on GPU.
Yeah, I mean, that doesn't surprise me. And same thing, there's issues with the PennyLane notebooks. And were you able to get it work on any of the other models? Yeah, so it's just one of those things. It's like, I think Qiskit should spend a lot more time on it, because with all the news, the Sandbox AQ, BASF, these huge companies, that they're basically saying like, we need quantum physics, on GPUs. It's reliable, it's readily available. It doesn't have like 4 or 5 other issues that, other options have. And the most recent one was this Monday with the generative AI is that, Eric Schmidt, Google Eric Schmidt, he came on, and Eric Schmidt came on, this is a post that they did. And, it said, oh, it's different than generative AI or any other classical process, that there's a benefit, in their eyes, in my eyes too, of running quantum physics on, GPUs. So, but yeah, the more that this happens, and we'll kind of advance. Were there any other questions?
I think it's rho big, like the Greek letter rho.
Yeah. Yeah, it's
R-H-O.
yeah, it's Robeg. So anyway, it helps to read all this documentation. So set every optimizer, so you can see on the screen the COBOLA, it's got, see at the top, and it says all the different things that can be changed with it. Obviously, it's, always the learning rate. I think the Qiskit atom optimizer, I couldn't find the exact weight decay, but that doesn't mean it's not there. And, this is just what I saw, up front. So, okay. Any other questions? So we're going to start to get into the PennyLane. And this specific model, so you'll see at the bottom, is I did a full benchmarking on it. So I switched everything to 25 qubits to get the complexity up. And like I said, when you're running low things, say for instance, this lightning.gpu, first the demonstration, this model close to 2 seconds using adjoint, so this is a differentiation method, that PennyLane has, that when you can, you definitely want to use it. 1.61 seconds, and then with the GPU, 1.21 seconds. So, like I said at the beginning, it's not hard to use lightning.gpu. The biggest steps is that you have to select a GPU on Colab. I don't know if there's an equivalent to the consumer models like locally, but this is the industrial, GPUs on Colab. You select A100, you change it to lightning.gpu, and then you do that pip install that I gave before, and that'll give you a single GPU, right? So the moral of the story here is that you have to make up your mind, like, how much more important will these set of experiments, can we always afford to run GPU, GPU quantum simulator? And I've had some of these models where it's 20 seconds for GPU based simulator, and it's over 300 or 600 seconds for CPU based, for the worser of it all. And then say a better CPU base is like 130. And 130 seconds compared to 20 seconds is still a huge difference, like if you're trying to do stuff. So yeah, so basically this was a benchmarking, and basically the time went down to about 1.2 seconds, with the lightning.gpu. Okay, this is an NVIDIA lightning.gpu. Okay, so this next one, what I did initially is I doubled the qubits and I got better random models. So the random models are not trained yet. So it means the parameters are randomized. Now, I was able to further improve that by changing this to QML.ry. And, it was either RZ or RX before. And you could see the improvement in the random models, right? So these weights have not been trained, they're just randomly assigned, parameters. And I think it's based on seed for those. But you can see these two bumps both got a bump by changing that gate right there. So this next one, basically, it was a different. So I doubled this circuit size to get this, basically the standard went up, a lot earlier here. Now, what happened here is basically the symmetric at certain points was benefiting from it. And I used an HRY, which is Hadamard RY, non-trainable, plus this double circuit up here for different accuracies, right? So this is a little bit harder for me to improve it much more. Again, sometimes you're limited by the data set. And as you get better with it, you keep going back to these and keep making them better. So this specific one, initially I removed these, they're called icing layers, it's ISINGs. And then basically with a smaller circuit, for training sets that were lower in number, so say for instance, this blue line, especially with this orange line up here, it was better, right? But typically, your bigger quantum circuits, figure, bigger data, that type of stuff. And what's shown by the curve down here is that this blue top line, reached the 1.0 quicker than the other two. And then pretty much, yeah, all of the other ones going down to green looked like higher accuracies, with the bigger circuit here. Okay, so this next one is basically, it's trying to fit the green line to the blue line. And initially what helped was to just, I'm calling it parameter bumping. So I've used it in other models too. And it's basically when you have an angle or a specific, parameter, or it's going to be a rotational angle in quantum parameters. I bumped it to 0.1 and the loss went from 0.51 down to 0.863. So a pretty good reduction. And this is seen because the green dots are basically closer to the blue line. Now I did that again. So I bumped it this time by 0.2, up by 0.2, and then, a further reduction in loss, not as much as before, but to this 0.259. And if you steer closely enough between this one and that one, the green dots are going to be, lower in loss, meaning that they're closer to that blue line in the specific one. Okay, so this next one is basically many body problems, but I think in specifically, is it shadows? I believe, yeah, shadows on this specific one. So first I gave it a speed up. So I just went default.qubit to lightning.qubit. And again, it's not always guaranteed that you're going to get a lot better, but some models is literally like, twice as fast. Just try the lightning.qubit up front. So you see that time, go down to closer to 200 seconds. So that was time. So this time I focused on, or this specific study, I focused on this, changing this green number, which I believe is a type of shot. And so anyways, I increased it to 10,000. So this is in the middle of the model, before it goes on to other things. And there's, this is basically at 0. So there's none of that deviation, on the edges here. So it's just, that's the goal, is basically whiter with that one. Okay, so this next one is basically without quantum memory. The stock model is all these like blues over here and the yellows here. Now, if I change the ratio of in primitives, so meaning that it's going to use less, say, like C0 gates, I think that's what the case is in this. So it's less of these 2 qubit gates. I'm able to get the blue dots isolated here, and then the yellows are definitely pushing over there. So it's just one of those things. It's just like, there's sometimes that all this other entanglement helps, and there's other times where it doesn't. And on this iteration, basically I used lightning.gpu to get this, the fastest time. Well, let's start at the bottom here. With the default.qubit, it's 197 seconds, okay? So this is a model you definitely want to switch to lightning.gpu. Now, a V100 GPU, which is, well known across the world, got 35.17 seconds with the lightning.gpu. Now, if I switched it in Colab to A100, which is top of the line in speed, and then you can go up higher in memory, but I didn't need it in the specific one, 27.52. So, that's what, like at least somewhere around there, like 5x speed up, from say the V100 to there. And then you kind of weigh these things in your head. So the V100 is over half the cost of an A100, but it's only 20% slower. So then that's, you put all these in a chart. And anyways, many people like NVIDIA has run many of these V100s with a smaller portion of A100s just because they're not that much slower. But when you need that extra boost in time, then, A100. Okay, so this next one is basically this is to use in other different models. So they're called MPS tensor networks, and this is some of the news from Monday too, from Sandbox AQ, is they want to use tensor networks. And basically, you know, their original one was a 4-qubit block. I drew a 10, and there's like, I think 3 different values that you have to change. Anyways, I'll have the notebooks up. I don't know about tonight, but in the next couple days. So if you're looking to do this kind of stuff. Now, the other thing is that you know, this is the first configuration. You set it to wires, and then there's some other things that are unique to tensor networks, some of the other values. But here's a 20 qubit at the bottom, and then I drew it in PennyLane. So as you can see, it's somewhat of a sketch, but it's better than their other sketch one. And many of people grow accustomed to the Qiskit, you know, the composer. And that feature, I don't think, is working too well right now to do that inside a PennyLane notebook. So here's a color version with 20 qubits of the tensor networks. And here's the next one. So basically, it's expansion strategy. I changed to, and it you know, ran a little bit faster. Now, I think the more compelling thing in this one is when it's same thing with number of qubits with frequencies, is that when I go from 5 wires to 7 wires, it's 2 to the n. So it's basically 32 frequencies for 5 qubits, or 128 frequencies for 7. And as you can see, there's a lot more going on with this Fourier spectrum. So, you know, that was interesting in that specific one. Now, this is another quantum GANs. So I'd say, I think Qiskit has a GANs, quantum GANs, and then PennyLane has at least two models in it. And on this specific one, I was able to get a different output by increasing iterations. So for this specific one, the loss, in general, the generator loss has to go down, okay? The images are what you want created, so you want the loss of those to go down. And a lot of times the discriminator loss will go up, and that's not always an indicator of image quality. So these 600s are similar to the 500s that I did before. I took it for another 100 iterations. But, you know, sometimes you think you have this figured out, you know, the generator loss is going down and discriminator loss is going up. And then you check the images and they're not very good. So anyways, there's other things working with that. But in general, I think that a lower generator loss is typically better. Okay, so this is basically unitary designs. This is one of it. So when you see default.mixed, this is PennyLane's, it's got noise in it, basically. Like quantum noise to estimate that type of stuff. And also there's things in the classical world called bit flips. And a bit flip is basically, it goes from a 0 to 1 or 1 or 0. And they're not very common, but in the quantum hardware realm, they're very common. So basically, I set the flip probability to a lot lower. So this event, this not wanted event, doesn't happen quite as much. And then you'll see that all three of the fidelities go up. So it's like 98, 98, 98 and change. And then these are all 99 and change. So that's basically, something to do on that specific one. Now, this one's interesting. And here's the case in primitive. So in primitives, I believe, are typically these 2 qubit gates, and probably above that too. It stands for not primitive. And basically what I did here is I changed from control RZ to a C0 gate, and the dots stay the same. However, the islands, like these land masses, they look like, on this specific one, it curved around to get that red dot, okay? So this is what you call like an experimentally determined result. And you always have to run experiments, even if you are more confident in theory. You always have to run. And in this bottom one, I doubled the data size, and I also tripled the layers. So this specific one, this specific one is 6 layers. This has more data points. So these bottom two, the data points are in the same spot. And as you can see, there's some red in the blue or the ocean, and there's some blue on the land. But when I increase the number of layers, you can see all the blue are in the ocean, and then all the red are in the land. So that's what did the trick there. And so they say, you know, this accuracy of the kernel with random parameters is, you know, 1. Okay, so this next one is basically distribution of, you know, data points over a, you know, the qubit sphere. And there's a limited amount of things that you could do with this specific model. So again, I did a parameter bump, and it puts the, you know, the data in a different configuration over the sphere, you know, the block sphere. And I did another one this time. So this is basically, you know, phi minus 2, omega plus 2. And then, you know, it's a different distribution of data. You know, it's the Haar measure is what they call. And, you know, these are all the ones out of the quantum machine learning ones. They have other demos that just, you know, don't run as much, or I should say they don't configure as much. So there's a mix, but most of these demos configure. So for instance, in this one, so we have a learning rate. So this is just, you know, universal to classical machine learning too, is I doubled the learning rate, and then it got a little bit faster, but it also changed the loss landscape a little bit, you know. So, you know, they reported similar, but the one on the left is probably preferred, right? As far as this X not going off the, you know, the dark blue. And then what we have here is I doubled the nodes. And then in this specific case, it didn't seem to change too much. And, you know, as far as like initial and final point in the loss landscape. And a lot of these demos, they're just, you know, they represent a lot of like they represent a field, right? So they're not going to have everything that, say, for instance, the classical, you know, graph networks, these types of things would have classically, but they represent a large amount of information. And, you know, basically you can, you know, change these things and do more with them if, you know, if you have different data sets, those types of things. So here's another case of the imprimitives. So basically in this specific one, if they don't mention it, it's usually a C NOT gate, which is a controlled NOT gate, which basically it controls the initial wire. And then the final one, it's going to flip if a certain condition meets with that. So in a control Z, CZs are probably the second most common 2-qubit gate that you'll see. And you'll see that, you know, the loss was lowered a little bit, you know, represented by the curve. And what I choose to do with this specific one is benchmark it. So say, for instance, between a CPU-based lightning qubit and parameter shift, which is the worst case scenario. Like you never want to run parameter shift on a simulator. 367 seconds. And then say, for instance, on the A100 lightning GPU with adjoint differentiation, which is the best case scenario, you know, 44 seconds. So it'd also be interesting, and I have to see here. I also ran 30 experiments to kind of coincide with this, changing different primitives and all these different configurations. And that's already up on GitHub. But the specific thing with this is like, what if the lightning.qubit was run with adjoint differentiation? What would that value be? It would be a lot lower. But like I said, like as the problems get harder, or, you know, the data sets get bigger, these types of things, is you'll start to see that differentiation between a lightning GPU and a lightning.qubit, which is a CPU. Okay, so this next specific one, so it's basically quantum nodes into Keras layers. And what was changed on this is I've had issues running this because it generates some warnings, but it just, everybody else is getting that same type of stuff. And it might be fixable with a certain version of TensorFlow. But basically, the modification, you know, for the more recent one has a classical layer followed by 4 quantum layers. Now, what happens here is the quantum layers, it's a circuit, and then it gets converted back into the classical equivalent. And then it's basically running, you know, this the end layer here, this dense layer. So what was improved with this specific one by changing this is the validation accuracy was higher, from 84 to 86%. So this could, easily turn into its own field on its own. Now here's the PyTorch equivalent. This model runs silky smooth. So this one's it's one of the faster models that I have. And so, I think it's Thomas did a really good job with this specific one. So initially what was done is adding 2 more quantum layers. So a quantum layer representing a quantum circuit, but it's effectively, in binary. And then this can be run in it should be able to, as long as you have PennyLane running in this PyTorch notebook, you should be able to run it in any PyTorch notebook as long as you have the settings correct. Okay, so a lot of times you'll see there's there's a forward pass and these types of things, and those have to be correct also. But this is like the bulk of it right there. Now, what I did in this specific one is I wound up with an angle embedding, and like I said, like an HRY is a terrific embedding layer, and it had a Hadamard gate followed by a rotational gate, non-parameterized, just embedding. And anyways, it wasn't liking the Hadamard gate, so I did an angle, and then I kept adding more angle embeddings to it. And then all of a sudden I get 99.5%, which is over the 86%, which I got. And then the authors is 85.5%. So these types of things, like I said, it's going to probably be years until, the physics of or quantum mechanics and qubits and data sets is more completely understood. As far as like recommending like an awesome circuit right away, and, based on that data set in seconds, these types of things. So anyways, I experimentally determined this one. And like I said, accuracy over 99% by doing this. And then this fits into this upper right hand. So this is the bottom left is your typical PennyLane circuit. So you have to have a qubit. You have to have, this is the simulator default.qubit. You have to specify how many wires. So wires is, another name for qubits in this case. And then you can also, this is where you specify CUDA, device. So sometimes you start off as like a device or CUDA. And anyways, these are the quantum gates right here. So this specific thing, say the Q node, here is the quantum circuit. Okay. Okay, so we're at, okay. So are there any questions? And we'll come back for specific slides, and then I'll kind of go through these. But are there any questions with, some of the more recent ones?
I have a question about this one. I can see that you got this angle embedding, but there's no entanglement between the layers.
Yeah. So if you watch a lot of these videos, Maria Scholl, she says sometimes you don't even need embedding. So yeah, entanglement is not always the best thing to have. Like what's happening is you'll have data sets, and they'll be mapped at different parts of the simulated qubit. And basically that effect is more important than entanglement at that point. So it's not just speed, or it's not just, other quantum effects, but yeah, like you can go pretty far with a good embedding.
Thanks. And
like I said, the quantum metric learning kind of took it to the nth degree. So this is like Seth Lloyd and others. And, the issue that they had is they get some overfitting. And there was a model out for it, but that was the concern, is like, people don't know how to correct for the overfitting. Any other questions? Okay, so this next one is basically, so quantum models is Fourier series here. And basically, a lot of times there's just a push to see if something works. So this is the whole, they'll call this left one, say like for instance, like a W, or it's like a sandwich. So you have a training layer an embedding layer followed by another training layer, and the weights or the parameters, like these knobs, like the actual values that get adjusted by the optimizer for machine learning, will be different for the weights at 0 versus the weights at 1. And then I just took a more approach, direct approach, and I just did embedding layer followed by a trainable layer, and that one worked out really well. So as you can see, it's like about an order of magnitude lower loss in this specific case. And what I found with other things too, and I've done layers as far as like 1 all the way up to 10, and it's usually about like at 8, like 8 trainable layers if they're just like single rotational gates. That's a good spot to be at. So I just did 2 in this case. So it's just like that upper right hand one. But now it's embedding trainable layer plus trainable layer. And then in this case, the loss was decreased a little bit. So like I said, it's always safe to just try a good embedding. A lot of times on Qiskit side, it's like a Z or a ZZ. In PennyLane side, it's like a HRY or, you could just do a layer of Hadamard gates and then, angle embedding, rotation equals Y, those types of things. But always try just the embedding, because a lot of times once you start to get into trainable weights, there's other factors going on, and you kind of have to, in my experience, you have to search for the correct number of one of these trainable layers to put in. It could take more time basically. So in this specific one, initially I set the step size at 0.3, and it turns out that this was not the dominant factor to produce basically the best, they're calling it learned weights versus target weights. So for those of you who don't know, so quantum data, if we could have quantum data, for simulators, devices, these types of things, it's preferred, because then you don't have to embed at all. So how I've been talking about focus on the embedding, well, that's if you have like a classical image that needs to go into quantum states through an embedding layer. So instead, if you have quantum data like this, it's known that it just doesn't last very long, maybe microseconds, milliseconds, stuff like that. So this particular demo has a feature in where you can set it. So I'm setting the maximum time for quantum data in this specific case to twice as what it was. And instead of 6 of the 8 compared to that, now 8 of the 8 are better than the last run. So these 0.56, 0.56, and it's closer by like an order of magnitude than it was, So these values, 1.24, 1.28, 1.67, they're closer than, trying to adjust for the step size. But, there's like a lot, I would say at least a coursework of stuff in the PennyLane QML demos, right? To not only understand it, but to improve it, to teach on it, that type of stuff. Now, this next one, a lot of people have run on, and I've optimized this a lot too, and it uses a truncated MNIST data set. So what happens here is that I just doubled the wires, and you can see the accuracies got up, and their initial setting, the classical actually outperformed the quantum. Now, my experience with this model is that it kind of goes back and forth, but the quantum typically had lower loss. So say, for instance, like this one's accuracy too, and it's winding up at, I think that's 83% versus 80%. And anyways, that's just the trend, right? Is that typically the lower loss model was the quantum. And this is it was a cool one to experiment with for sure. The other cool one is coming up here too with a quantum transfer learning. Okay, so this is just like, even if you're coming from deep learning, ensemble learning, it's basically, it's trying to get the most juice out of each specific device. So say, for instance, like if you had like, a CPU device over here that used different transpiling than this one over here, those types of things. But anyways, the stock one was Rigetti and a Qiskit.err. And the accuracy is 0.824. Now, I think it's mostly because of the way that, it calculates math. I don't think there's anything particularly wrong with it. Last time I had changed this to the default.qubit and the circ.qsim, and then got a little higher. And then this time I wanted to see speeds, right? So benchmarking. So then in specific, I benchmarked this, and then this is basically this upper right hand one, 5.5 seconds down to 4.27, switching to lightning.qubit. And this is an iris data set. This is small, right? This is like 150 images. That's why it's fast. And then next with the lightning.gpu. So, 0.17 seconds, better with an A100 lightning.gpu. Probably not worth it in this case, but it'd be worth running this on a lot bigger data set for sure. Okay, so this is probably the most popular model. This one came out in 2019 by Andrea Marie, and I don't think he's at PennyLane right now, but it brought in a deep learning neural network classical plus a quantum algorithm, and then the deep learning neural network pre-trained from ImageNet, carry in those weights. Typically the frozen part was the classical neural network from those pre-trained weights, and then typically you would train the quantum gates with a specific one. So as you can see, better test accuracy. So in this case, I have had other ones where including an entangling layer did go up, and it's actually one of my highest. However, when you get up to this is like 300 or 400 images, when you get up to thousands of images on these GPUs that are 16 gigs, 40 gigs, I had no way of using a certain number of qubits with an entangling layer, so I did the best that I could. And as you can see here, so a little bump in accuracy without the entangling layer in this case. Now, what the next step is basically is increasing the depth of it all. So the Q depth, actually, you have to be careful with this. If you try to do it your own way, you're going to skip out on some of the benefits of this is a variable, but other things in the model depend on this number. So say, for instance, if you want to set 8 layers, your gates on your own and not adjust this, first of all, it's set to 6, so it's going to be 6. But anyway, this is the correct way of doing it. So when you see layers, you want to search for layers, and you want to search for depth. And before you start adjusting things with the circuit. Okay, so there's an issue right now. I can't run a GPU on this model, but I ran it with CPU, so I got a little bit better bump. And this one makes sense, right? So up from 86.9% to 90.8%, more depth. And that'll be the trend in all the quantum machine learning. Similar to classical deep learning neural networks, they do not like to go wide. So they don't like more nodes. And it's the same thing with qubits. We don't like more qubits. So essentially, qubits times outputs or nodes times outputs is the disadvantage of having a wide neural network. Okay, so that's why they're called deep neural networks. Okay, so for this next one is interesting. So this is basically it's a photonic simulator, and the cutoff dimension is the number of dimensions you'll allow. So whether it's 14, 15, like that. But basically increasing it last time decreased the cost. And then also with this, what helped is increasing the layers to 6. And then, basically this is decreasing the cost a little bit more. So you see 9381 and then 9355. Okay, and then so this is the other GANs. So this one's very interesting, and there's been a lot of time and effort that go behind these models. So we should thank, especially with the holiday, PennyLane and other researchers, for putting these together. If you could understand all of these, end to end, you're doing pretty good. So in specific, they start off with a circ.simulator. This is known to be a lot slower, and actually the way it transpiles or the way it deals with gates is not as effective as Google circ.sim. So or Google circ.qsim. These are both Google simulators in a PennyLane model, in a Python notebook, right? So you can access these other ones too. Okay, so you'll see here, so the probability of real classified as real for the discriminator, remember there's discriminator and generator, is better, 98.858. It's just a little bit, right? It's splitting some hairs, but the main thing was the speed, right? So 30 seconds down from 47. So on that specific one. And then I took the benchmarking a little bit further. And then so I did it with lightning.qubit. And then all of the PennyLanes have very similar, accuracies, right? But the times differ. So say, for instance, like 11 seconds for the lightning.qubit, and then down to 10 seconds for lightning.gpu. Okay, and then so this is data re-uploading. This is a promising method in quantum machine learning because basically you can use a single qubit or qubit. So qubit is 0, 1, qubit is 0, 1, 2, 3, and you can go up to however many. And anyways, if you're limiting the number of qubits or qubits or whatever, then you're not getting into that wideness problem that deep learning also has. Okay, so if we can get awesome accuracies, understanding quantum physics, the whole type of stuff, bigger data sets. So anyways, I decreased the learning rate. So with this specific one down to 0.48, I think it was set to 0.6. And then, basically better test accuracy on this specific one. Very common, modification. Okay, so this is the last of the models. Okay, so the demos. This is variational classifier. I've had other PennyLane researchers said to focus on this one. This one seems to have, it's not quite as interesting, or maybe not quite as complex as the quantum transfer learning as far as intellectually, but this one they say on a performance basis focus on this. So originally increased the number of layers to 8, decreasing the cost. And what happens here is this black dotted line changes. So you can see it's like it curves up like that, maybe like convex, you could call. This is more straight. Now, if I did it with 10 layers, basically it curves in the other way. And essentially they say the cost is better here too. And with an A100, it's 259.78 seconds with the GPU. With the CPU base 278. So again, like always, number one, build a model around a GPU working. And then the other thing is if you're dealing with existing models, always make sure that the speed, is going to benefit the cost of running GPUs all day. Okay, so here's a couple quotes here. And basically, these are Cicero researchers. This is a big paper. It's Quantum Inspired Machine Learning, a Survey is the name of the paper. QiML represents a multifaceted research domain with investigations pushing to exceed conventional classical state-of-the-art results or exploring the expressivity provided by quantum formulations, okay? So that's more like, I think classifications, better accuracies type of stuff. The second quote is, as QiML continues to evolve, we anticipate a wealth of future developments drawing from quantum mechanics, quantum computing, and classical machine learning, enriching the field further. And of course, this would be on classical hardware. And then this last one by Jack Hidary is basically, it says we don't have to wait for a quantum computer. We're not using a quantum computer, but we're using quantum equations, quantum software on GPUs. And that's a big breakthrough, is that's that specific one. So before I switch back, any specific questions regarding the slides? So we can go back up to the photonics. And again, I want to stress, I could go on to a lot of the Xanadu questions regarding to photonics and answer them kind of easily. And I don't know too much about the field. And I don't know how much has advanced in the past 5 years or whatever. But I thought graph, it'll say, let's see.
I had a slide about there was the slide before, which was about convolutional neural networks, where There was an improvement with the number of qubits
Yeah.
in Menis data. Of course, there's a question whether improvement is because we have less loss on preparing Menis data through PCA, or was it because we have more qubits? It's very difficult to measure which one contributed here.
I mean, I can understand it a little bit better on the quantum transfer learning, because it's literally the way that the elements come in and like the inputs, outputs, that it's like, if it's a 2-class data set, you use 4 qubits, and that's the best. And then sometimes you can bump up to 8 or whatever. But, you know, sometimes it just depends, because like you'll just run a bunch of experiments and it'll be like, you know, you weren't expecting that. Because say, for instance, like my best 8 qubit for this one, I was able to, I think it was the betting was 4 qubits, but the rest of the ansatz was 8, you know, and it still gave me the best results. So I have all this on GitHub too. So it's under, you know, it'll be under PennyLane. And there's a separate folder for convolutional neural networks. And there's also a folder for, you know, the upper right-hand one too. But yeah, I think the biggest overarching thing is the inputs, outputs, because I have a 44-class data set that I can only run to 20 qubits based on the number of images and how much RAM I have. But my best performing is a 10-class, and I run that on 20 qubits because I can. And, you know, 80 plus, you know, high 80s, you know, an accuracy for 10 classes. So I think that the biggest thing is the way that the circuit is lining up with the rest of the model. And like I said, most of these are, you know, 4 qubits. You know, this is, let's see, trying to think if they use the full MNIST data set on this specific one. Because a lot of times they'll just truncate, right? Like even if it's 10 classes, like 0 to 9, like 0, 1, 2 up to 9, they'll just cut the number of images down, that type of stuff. But yeah, it depends on number of classes, you know, your inputs, outputs, that type of stuff. And this would be a good model to study. You know, it's been out for a while, just like the quantum transfer learning model has been out. But this and the quantum transfer learning model would be good to study as far as, you know, what exactly you can do. I was mostly limited by classes, you know, and I understood enough kind of what was going on in other parts of the model.
Thanks.
Yeah. Any other questions? And we are seeing, you know, the new wave, and definitely there was an initial wave when these came out. You know, I think more because there's other models that use both a classical neural network and it also uses a, you know, quantum algorithm. And I don't know if it's just presentation or number of, you know, GitHub posts with this, but definitely the, you know, the quantum transfer learning model was, it was a big hit. I've had issues. Ultimately, you want to train the classical learning network, say with a separate optimizer, and you want to train the quantum circuit with a separate one. And PennyLane calls it end-to-end or all-to-all differentiation. So, you know, that, and, you know, there needs to get a little bit better PyTorch with the GPUs, that type of stuff. Any other questions regarding the slides?
I have a comment about the Fourier slide because I was doing a bit of experiments with it. So when you actually have a very simple data like a sine function, that works very well. But when you have more complicated functions like a combination of sines, cosines, or real data, they're very difficult to fit the data. So with this, that requires definitely more than 1 qubit because you could fit it nicely with a single qubit, but with more complex data, they're very tricky to work with.
Yeah. Yeah, I've been able to make, so say for instance, like the HRY, this embedding that I use PennyLane's, it was like, you know, how to figure out, you know, how it's fit to a function. And it's like the sine wave that represents the surface area of a sphere. i.e. a qubit, you know? So over and over again, that embedding, I can't say I use it many times in quantum transfer learning, but it seems like there'd probably be some more connections, you know, the industry can make as a whole, as opposed to just creating a brand new quantum circuit for every data set, you know, those types of things. But like all of this existed pretty much before many of us got into, you know, quantum machine learning. Like these demos, a lot of these have been around for, like I said, like the, you know, 4 years, you know, for quantum transfer learning, and then convolutional neural networks, I think maybe a little bit after that. So but yeah, I think that the point is to, you know, that we need to, you know, stay on the gas with it. And basically, you know, this is a working field, right? And we have Sandbox AQ and we have BASF and we have Classic, you know, partnering with a Israel hospital with NVIDIA and Terra Quantum. Basically, I know they've done a fair amount with hardware, but basically saying like GPUs, you know, how can we make things better? Awesome. Any other questions? But yeah, there's multiple effects, and going back to some of the chat, there's multiple different effects in quantum, because you have quantum entanglement, superpositioning, quantum interference, these types of things. And you know, I think the really encouraging thing is that it works, you know, because we have all these models that mostly work, except for just maybe one of these Qiskits, like the bottom half doesn't work right now. But, you know, it just works. And I think the field that's practical, and you can go through all this stuff with adjoint differentiation and pure states and, you know, no density matrices, and, you know, data sets can be, you know, treated on the on the outsides of the block sphere, you know, practical, available, you know, relatively cheap. I mean, there's going to be new NVIDIA GPUs coming out next year, like the H200s and probably A200s if I were to guess. But, you know, this is, you know, whether we have to use gate models, I don't know, for our architecture, but, you know, it just makes sense. Like quantum physics plus classical bits plus data sets equals new utilities, or, you know, better performance, maybe speed ups. It's going to slow down because of the simulated aspect of it. But yeah, and if you haven't read, definitely it's the Quantum Inspired Machine Learning, a survey, and it's the two quotes, those Cicero researchers. I would definitely check that out. Now, is there anybody that would like to have any questions or comments that we haven't heard from yet? So Walter or Dino or Gil, go ahead.
No, I'm good. No,
Yeah, good to hear from everybody, you know.
it's very, very informative. Very, very informative. It was a great talk.
Yeah, thank you. And then George or Edwidge?
It's a lot to digest, but this week I have a spare day, so I can look at more of it.
Yeah, and this might come as a surprise to many of you that haven't been on the past couple months, but in my opinion, it's easier for somebody in deep learning to come to quantum machine learning than for somebody in quantum computing to come to quantum machine learning, because we're talking about optimizers and, you know, loss functions and trainable parameters, regularization, these types of things. But it does help to know the circuits. Like I do have a background in the quantum circuit, so, you know, I know what good educated guesses are, right? And the more you read papers, you know, these things help too. Anybody else? So Diego or Mo? And then if it's just a happy Thanksgiving, that's fine too. Happy holiday.
Yeah, happy Thanksgiving. And again, it's a lot of information, but I'm processing it. So very informative. Keep it up. Keep up the good work.
Yeah, I appreciate it.
Yeah, thank you and enjoy a day off.
Yeah, I think tomorrow will be lighter. Just on the work side, but with the food, I don't know if I can still say the same thing. And, so I put the GitHub up and it's done pretty well so far. But if you or anybody else needs some holiday reading, it's there. I have other friends in different parts of the country. They say they get four days off. These types of things, there's basically, I would start with the code and then kind of work backwards. If you already can code, that's awesome. I think you'll get the most, number one, by running, and then number two, by teaching people, and then developing, on top of that. It's just it's like it's an invisible thing, but like not only that you're helping other people, but you have to think in your mind before you go talk to a group of people or a person, do I understand this? Like, can I understand, can I basically present this again? Those types of things.
I agree with that a lot. It was Richard Feynman who said, if you can't explain it, you don't really understand it.
Yeah. Yeah. So that puts the pressure on a little bit, but if you get comfortable, because everybody has, free time, fun time, holidays, that type of stuff. But if you just get used to that, as far as like, oh, okay, I'll push it this, I have to accomplish this today. And say, for instance, with this, I still have to touch up some things and put on the references, that type of stuff. But the quicker, I guess, other people that, hear you talk about, quantum and machine learning, and then you could start teaching other people too, right? So just run all the demos, a couple months later, come back, run them again. The Xanadu discussion is pretty good, because it's actually really good, because they're the researchers that some of them actually make these demos. And I wouldn't press them as far as saying like, hello, person who made this, because that tends to get somebody else. But if you ask like a very complicated question about it, then you might have a better chance of getting the original author. But in all this stuff, it's developmental, because I asked about two of these. Why am I getting these, certain messages for two of the TensorFlow ones? And anyways, in a different demo, I found that I'm using a different TensorFlow, so I can go back and try that again. But anyways, as far as the field goes, we have a number one, for quantum machine learning, the software, like the platform, the library. I think in any field, it needs to be a better, say, like number two, like where they're fully engaged, they love quantum machine learning, how we see it today. And even a number three, because we have Qiskit and, TensorFlow Quantum and Torch Quantum. And there's other ones too, but, when the rest of the field, like it's like the PyTorch and the TensorFlow, then you have JAX and, these other ones too. But the more we can get from the other parts of the industry, I think the better off everything will be. Awesome. Any other last questions or comments? It's probably getting close to Thanksgiving for many people. Hopefully you're not escaping, like from the family stuff, but yeah, any other last questions or comments? And then if not, pull this up here. I always get a question about, yes, I still got 2 casts. I'm getting better. Yeah, I appreciate everybody coming on. And this has been discussion 110 for 38 Qiskit PennyLane QML/QiML demos for Thanksgiving Eve. Again, happy holiday, happy Thanksgiving to everybody. This has been November 22nd, 2023. Have a productive rest of the night. Again, I should have most of this up in the next couple days as far as the code, and have a productive rest of the year. Yeah, hopefully I'll see you next week. Okay, take care.
Thank you, Kevin. Have a good Thanksgiving.
All right, thanks everybody.
All right.